hydrated compounds. When you see the word hydrated, what do you think of? Water, yeah. So these are chemical compounds that always hang around some water, all right? They have groupies, all right? Depending on maybe, I don't know, how popular they are. They have more groupies or less groupies, I guess we could say. But so for example here, this is copper 2 chloride, and it has 2 water molecules that always hang around it, all right? Now, how would we actually like write this as the words, the nomenclature of it? Well, the new part is just how many hydrates you have. So in this case, there's 2, so it's dihydrate. And then we just use the regular nomenclature for the other part. And in this case, it's copper 2 chloride. And it's copper 2 chloride because it's a transition metal. And then chloride is -1 and there's 2 of them. So this has to be +2 to balance it out, all right? All right, now another thing with the hydrated compounds is, you see this dot here? This dot means in association with, all right? Meaning they're always together. In math class, the dot means multiplication, right? In our class, it means in association, which means you add them together. So it's a little bit confusing, but when you're trying to figure out the molecular mass, you do what we did before. You figure out this part, you figure out this part, and then you add the 2 numbers together. And that's it, all right? Then you have how much its molecular mass is. So copper is 63.55. Chloride is 35.45, and there's 2 of them. So you can figure out this part, all right? Figure out what that is. And then you figure out what water is. Now the cool thing with hydrates are, there's always going to be a multiple of water. So if you want to, you can kind of memorize water's molecular mass, so you don't have to do the work for this each time, all right? For example, it's 1.01 times 2, because there's always 2 hydrogens in oxygen. 2 hydrogens in water. And then the oxygen, there's always 1, and it's 16.00. So when you do this, it's always going to be 18.02. All right, so the molecular mass of water is always 18.02 grams per mole. And then here we have 2 of them, so we would multiply that together. All right, so we add up the copper 2 chloride, we add up the water, and then we'll get the total molecular mass for the whole thing. All right. Which is 170.49, is that right? Make sure. Okay, so when heated, these hydrates can lose their water molecules. Then they're called anhydrous, which means without water. All right, so they lost their water. All right, and how do you think we could heat them up? Hot plates, fire, Bunsen burners, that kind of thing. We can just heat them up. And we'll do a lab later on where we actually do that, where we take cobalt 2 chloride hexahydrate, and then we heat it up so that all the water disappears, or doesn't really disappear, it evaporates off, boils off, and then you're left with cobalt 2 chloride anhydrous just by itself. How would we know that the water left? Is it going to weigh more or less? It's going to weigh less, right? It's going to weigh less because the water's gone. So this one will weigh less because the water's gone. Also, this is really cool because it goes from a purple, a dark purple color, to a like light blue color. So we'll actually see a color change happen when we do this in the lab. All right? All right, now this is what another kind of problem would look like for a hydrate. All you're trying to do is solve for x, all right? Just like in math, right? So all we want to do is figure out what the hydrate is for this hydrate, all right? And that's what number 4 says. It says, what is x and the mass of water? All right, so the mass of the hydrated compound, which is the total, is that. The mass of the anhydrous compound is this, all right? What is the formula for the anhydrous compound? Yeah, Jojo. Yep, exactly. CuSO4, all right? What's the formula for this one? We don't know, right? We know it's CuSO4 in some water, but we don't know how much it is. What else can we figure out from these two numbers? Right?
The mass of the water.
Yeah, the mass of the water. How would you figure that out?
Subtracting 1.023 by 0.61.
Exactly. So if we subtract these, we'll get the mass of the water, which is 0.369. All right, because this top one was both the CuSO4 and the water. We just don't know how much water. All right, now, the rest of this is very similar to empirical formula. So if you remember empirical formula, the first step was to go from percent to grams, right? In this case, you're already in grams, all right? Because we have grams of this and we have grams of this. We can't use this one because we don't know the full formula for it. But we do know the formula for this, so we could convert this from grams to moles, right? Same thing's true here. We can convert this from grams into moles. So step one, after you do the subtraction, so I guess we'll say step one is subtraction. Step two is going to be go from grams to moles. All right, let's do that. And like I said, it's like empirical formula. So step three is going to be divide by the smallest. All right, so let's do some math. All right, so the molecular mass of the copper 2 sulfate is 159.62, and the water is, once we do the math, we'll get the number of moles for copper 2 sulfate is 0.00410, and then down here we'll have 0.0205. Okay, did you guys get that? Yeah? Okay, what's our next step? We have moles. Now, just like empirical formula, we divide by the smaller of the two. So out of these two numbers, which one's the smaller? Yeah, the first one, right? Okay, so we divide by the smallest one. That's going to give us one of these up here, right? Which makes sense. The first thing should always be 1, okay? So when you divide these, you're basically getting the number that goes in front. So in this case, it's a 1, which we don't have to show, all right? Now, if you do the bottom one, when you divide here, this is going to give you 5, right? So again, that's the number that goes in front. So that means the x is going to be a 5. All right. So the final answer for the problem would be CuSO5 in association with 5H2O. All right. Yeah, Sam.
Why is it CuSO5 and not SO4?
Because I wasn't paying attention. Yeah, it should be CuSO4. You're right. Thank you. Any others? Good.